Here is another way to get a flavor of just how difficult it is to collect data, especially from the past, how to reconstruct the information with the data that exists. And there are various techniques used to fill the gaps in the past in space and time. Various statistical techniques, assumptions go into it, and so on. So even when the same raw data from the same locations for the same period are being used by different groups, some approximations can lead to differences in the information that gets derived from it. So here temperature data is used to derive anomalies with respect to a base period, and different groups are involved here. NASA, this is the UK group, NOAA, so that's another US agency, Japanese Met Organization, and Berkeley Earth Project, which is another US contribution. So you can see that in the beginning only Hadkrut and Berkeley have data. They are brave enough to go back. Others come in later, and there are differences, especially over here. And even at the very end, you can see that these are not necessarily small differences when you think about these are global temperature changes, global mean, and the energy associated with these small differences is not small, it's quite substantial. So obviously we need to be careful, but the idea is that despite the difficulties, we keep increasing the coverage, and as we go into the future, we continue to reduce the uncertainties in each product and the differences between them as well. This becomes even more complicated for the ocean, where the data in the past for deeper ocean is very sparse in time and space, and the coverage. So UK, for example, Europe and North America had great trade, so you would get a lot of coverage in the northern hemisphere. Southern hemisphere, there is much less land, much less ship traffic, and as you go into the Southern Ocean, the weather is so bad that nobody goes there in the winter. So satellites add some confidence later on, but you can see that the ocean heat content in 10 to the 22 joules is substantially different between these four products. I think it's the Chinese, Japanese, this is Australian, and this is US. And these are not, so if you look at the number of units here and multiply by 10 to the 22, that's a massive amount of energy that we are disagreeing on, and that continues even into the present period. So this difference here again is about 10 to the 22. So if it is 1 or 2 units, that's 10 to the 22 times 1 or 2 joules, which is quite substantial. So obviously these things matter in terms of energy budget and so on. So there are many ways in which these are dealt with, and there are other reasons to worry about as well. For example, natural variabilities like El Nino and La Nina confound the trends in global mean temperature. Why? We will learn later on that when the ocean is in a normal state or in a La Nina state, if you don't know what these are, you can look up my podcasts elsewhere, but we will touch on those here later on. Ocean is taking up a lot of heat from the atmosphere during a La Nina year. When El Nino comes, the ocean is throwing that heat back into the atmosphere, so there is a mini global warming. So there is a mini global cooling happening during La Nina because the ocean is sucking up the heat. So remember, global warming and cooling are the atmospheric temperature changes. So the atmospheric temperature can cool when the ocean takes up a lot of heat, and it can warm when the ocean gives back the heat. This is what we have to worry about when we think about how much heat is being stored in the ocean, because it's not gone out of the system. It is still within the system, hidden from the atmosphere, but still very much there, and can come back based on various processes and natural variability. Okay, so this just gives you a sense that during La Nina you get a reduction in the global average temperature change, and during El Nino you get a mini global warming. So you can see the 2015-16 was one of the massive El Ninos, 97-98 was another massive El Nino in the 20th century, and 82-83 was also a big El Nino. Big El Nino basically means how many degrees warming happened in the eastern Pacific around Galapagos, and we wouldn't usually care if something happens in the ocean, but when that much heat is being moved around, it results in so-called teleconnections. So rainfall over India, East Africa, western coast of US, South America, and so on change. Droughts, floods, mudslides, fisheries dying, seabirds dying. Lots of things happen during an El Nino and La Nina. That's why we care about it. But in this context, the data that we're collecting for El Nino and La Nina, for predicting El Nino and La Nina, actually can help with global warming monitoring as well. So just to touch a little bit on the Global Climate Network temperature stations. So obviously these are all islands and these are all land points, and you think, wow, there is a lot of data. So there are many that are historical sites, there are some that are still active, and you can see the length of station record changes depending on where you are. So some of them are as long as 150 years, some of them are in the range of 90 to 100 years, some are much shorter. So much of the ocean obviously is not covered by this network because you need islands where you can measure these things. So again, looking at the global warming pattern that we saw, where we saw that there was no warming or cooling happening here and there was polar amplification happening here, this data coverage is not enough at all, and sampling is very biased. North America and Europe are heavily covered, some parts of Africa and South America are heavily covered, some parts of Asia, but there are large parts that are not covered very well. Okay, so those matter when we are trying to derive long-term records. Ocean, again, much more difficult, but there are ship lines that you cannot clearly see here, the so-called volunteer observing ships, which are fit with thermoselenographs and other kinds of MBTs or XBTs, expendable bathythermographs, and so on, that measure temperatures and have long records as well. And there are many buoys that are moored. There are many scientific cruises that are done regularly, coordinated fashion or uncoordinated fashion. Countries may do their own things, and there are national, international programs as well, and so on. So again, the tiny dots here, for example, so-called Argo float, which are some things that go up and down. So they go and park at 2,000 meters. Why? Because any instrument you put near the ocean surface tend to get what is called biofouling. Things begin to grow on them and fish come by and the instrument can become dysfunctional. Sometimes poisons are used to keep fish and marine organisms away, which is, yeah, you have to be careful how much you kill, but nonetheless, Argo is an amazing platform that bobs up and down and sends data every few days. So each dot here is a tiny plate. If you put a real size, you will not be able to see it. So even though it looks like a large number, it's only a few thousand, and hopefully the coverage will increase, but they have added enormously valuable data to the database, and they are only about 20 years old now, but still they will hopefully continue to grow, and so on. So ocean data there. Of course, tide gauges are there as well. Satellites, this is not a comprehensive list of satellites, I'm sure, but I just took this from WMO. I'm not even sure how old it is, but I just wanted to give you a sense that there are national and international programs to measure temperatures, sea level, water vapor, clouds, vegetation, aerosols, gases like carbon monoxide, methane, nitrous oxide, all sorts of things, and of course to monitor sea surface and land surface for various things like vegetation cover, leaf area index. A lot of them are weather satellites, which tend to be geostationary, which means they go with the Earth, so they're always looking at the same spot, so that each country can have its own initialization for the weather forecasts and climate forecast. And there are international satellites like JASON and so on, which are so there are, you can see there are equatorial orbits, polar orbits, geosynchronous orbits, and so on and so forth. So it's a very, very vast field, remote sensing, but obviously we're just taking a quick look at it. So here you get a better sense of the variables. This is from the European Space Agency. Sea ice, sea level, surface temperature, ocean color, which is chlorophyll, ice sheets, glaciers, land cover, which is vegetation and urbanization and other things, agriculture, soil moisture, fire, ozone, greenhouse gases, clouds and aerosols. So this animation here should be able to work. I don't know how to turn it on. Okay, let me turn off the pointer and see if I can do it. Here we are. So it is showing CO2 increase, how we are increasing by a few ppm per year, change in ice sheets, so enormously valuable data for glacier elevation, Arctic ice extent, sea surface temperatures, and chlorophyll concentration, sea level, so which we mentioned with laser altimeters. This is the soil moisture. You can see the deserts, wet regions, irrigation, snow, ice, other things. Is there anything else here? No? Okay. So that's the idea. There is also very good data, lots of it online. The book gives us lots of links actually on videos and websites that report the data and display the data and let you download it, provides graphics, and so on. For example, you can go to the website on something called TAO, Tropical Atmosphere Ocean Array, or Rama moorings or Pirata moorings, and see what is the temperature in the middle of the Pacific just a few hours ago, because that data is constantly being beamed to the satellite, and some labs like the Pacific Marine Environmental Lab in Seattle displays that data, so you can go and look at it. So there is enormous amount of data being served online that you can go and look at. I didn't list all the websites that the book provides in each chapter, but since the book is free, you can download the book and go through it and make sure you look at a lot of the valuable information that is provided in each chapter. I'm just going to focus on the content and keep moving along. Okay, so that's the end of this chapter. Next we will come back to paleoclimate. Okay.